Hello everyone, welcome back to my channel AI Shorts. So in this particular video we're gonna see like vector quantized variational autoencoder, which we also call as VQ-VAE. In this particular video we will be using VQ-VAE. So we'll be going behind the intuition of the VQ-VAE. So we'll also go over how to generate the data, and after we have trained VQ-VAE model and the difference between the general variational autoencoder and vector quantization variational autoencoder. So if you see here VQ-VAE, instead of using the actual continuous values from the decoder, we will be using the vector representations which are from the code book present in this embedding space. So instead of using the actual continuous values of the latent vectors, VQ-VAE is used the indices of the closest code words from the code book to represent them, and this means that the latent space comes the discrete here. So which with the possible the latent representation being a combination of these code word indices. So this shared code book, so this code book is nothing but it's a learnable code words. So these consist of the vectors that evolve during the training to capture the most of the important patterns in present the data. The vector quantization layer in VQ-VAE is responsible for the mapping of these continuous latent vectors produced in the encoder to the closest code words in this code book. So this mapping is typically done by using the Euclidean distance as a measure of similarity, which we also called codebook loss and the commitment loss. VQ layer replaces the original continuous latent vectors with the indices of these code words. This effectively discretizes this latent space. So why we are going specifically to the VQ-VAE is that, so let's see a task where such as the image captioning, why this particular VQ-VAE performs better than the traditional VAE. So if you see, for example, we want to generate the captions for the given image. That VAE might be used to model the distribution of the latent representation of this image. So since the latent space is continuous here, so it may not explicitly capture categorical or symbolical aspects of that particular scenes, which makes it more challenging to generate the captions. So for example, if this embedding space consists of these embeddings will be pertaining to some of the words, for example, then we will be able to map them in a better manner, so that we can discretize this space and we can able to generate those images. In case of VQ-VAE, what we do is we will learn a discrete latent space in that case that explicitly represent this different categories or objects present in these images, and this discrete nature of this latent space allows more explicit control over the features and such as the type of the objects and the activities performed in this image. So in that way, VQ-VAE performs better than the traditional VAE. So let's see the different components of the VQ-VAE. So more or less pretty similar to the variants of the autoencoders, and the component that differs is an embedding space. So we call it as a codebook. This is a embedding space. Consists of the k embedding vectors, which are d-dimensional vectors using which will represent our data in this latent space. And the second component is the encoder. Since we are will be working with the images, and now it consists of the blocks of convolutional layers. It will take an input image and generate a feature map. Now let's assume for the time being that our feature map is a grid of d-dimension vectors, d being the latent dimension. So if the dimensionality of the encoder output is different than d, then we add one more 1x1 convolution layer to ensure that our encoder output matches with the shared dimensionality of that code book that which we are having. So now we need to convert this encoder output into our latent representation using this code book vector to do this. For each d-dimensional vector in this encoded output, we'll find a nearest codebook member, replace it with that codebook vector. So let's assume we compute the distance between the pairs of this encoder output vectors and the codebook vectors. We'll find that nearest member, and then our quantized model will be this. So our decoder side, we don't use the encoder output at all. But instead we pass the decoder, the quantized encoder output. This goes to this decoder, which in our implementation will be stack of the transposed convolutional blocks. It then generates the output from the back propagation using the reconstruction loss, which will be MSE. So once you train this network using the reconstruction loss, unfortunately the model will not learn much in this fact. So when you inspect the gradients of any layer before the decoder would be 0, the back propagation happens perfectly from the loss to the decoder. So but at the point where we find the nearest embedding vector, the gradient would become 0. So because we are taking the argmin between these two, the latent representation and the codebook embedding. So to update these embedding vectors, now given our codebook vectors like representation of the latent dimensional space, so we can look at them as a being centroids and regard a whole quantization operation as a clustering between the encoder outputs and the k clusters. So it's easy to update the embedding vector, bringing them closer to these encoding points. So assign them, and we would update the mean of this cluster, so which would be we'll be doing with the codebook loss. We will also use a loss called commitment loss to ensure that the embeddings are constant and bring the encoded points assigned to them closer. So the authors mentioned that this loss is meant to ensure that the encoder commits to an embedding and prevents the encoder outputs from fluctuating between the different code vectors. So it brings the stability to the training, both the commitment and the codebook loss. Now let's go through the code. So this is the VQ-VAE code, and we also have the encoder, decoder and quantizer code. So if you see here VQ-VAE code, we have written this code in the PyTorch. So like we are defining the encoder module here. So let's go and see what we have in the encoder. So encoder, and these are the different activation functions that I am using here. Like generally in the transformers, the latest popular function GALU is being used, and we also have a activation function called sigmoid linear unit, which is similar to the sigmoid. And what exactly we do is, like, we will be convolution layers stacked. So for where each convolution layer followed by the batch normalization layer. So in these encoder layers, we will be having the sequential layers which involves convolution layer and batch normalization and the activation map based on our configuration. And we also have the another convolution layer in the encoder. So we perform the forward propagation here. So this is the encoder block, which we will be getting the latent representation from the input. And if you go back to VQ-VAE, so then once we get the output from the encoder, and we also have this pre-quantization convolution which we will be doing. So this is the 1x1 convolution to reduce the number of channel and to match the codebook vector which we are having. So now we are also having the get quantizer quantizer module. Yeah, so if you can see here, we have the embedding layers of the codebook size, based on this codebook vectors and the latent dimensions. So we'll be performing the we'll be calculating the pairwise distances after permutation and reshaping, so that we will be performing it over the last dimension. So we'll be calculating the distance between the encoder output, which is the input for this particular block, and the embeddings which are present in the codebook vectors. And based on this, we will calculate the indices where the minimum distance is present. And once we calculate the minimum encoding indices, based on this we perform the assignment. So here if you see, we calculate the commitment loss and the codebook loss between the latent representation and quantization output. Then we perform the back propagation through this quantization, and so then we will quantize these indices. So going back to our main code, so we have performed the quantization, and we will be also having the 1x1 convolution post quantization. So here then we will pass it to the decoder, where we will be calculating the reconstruction loss. So if you see here, we are performing the forward propagation, where we will be having the encoder, and we will pass this encoder to the pre-quantization. And once we get the quantized input, then we will be performing the quantization and calculate the commitment loss and the codebook loss. So then after which we will be again performing the 1x1 convolution to pass it to the decoder. These are the different losses. So this is how we perform the encoding and decoding process in the quantized variational autoencoder. If you like my video, please subscribe. Thank you so much.